Hello again friends. In the previous session we started with the lock variable synchronization mechanism. There we discussed this lock variable mechanism does not guarantee the mutual exclusion. It guarantees the progress, and again it does not guarantee the bounded waiting. Similarly, all the requirements of synchronization mechanism we are going to discuss in this next synchronization mechanism, which is strict alternation. Alright, let us discuss the characteristics of this strict alternation mechanism. The first characteristic is it is purely a software solution, means it does not require any support from the hardware. The second characteristic is this mechanism can be used only when you want to synchronize between two processes, let's say P0 and P1 only. In other words, you cannot use this solution if there are more than two processes. The third characteristic is this mechanism can be implemented purely at the user mode. Let's say in C, C++, Java, any language you can write this program at the user level, and you do not require any kernel level support for implementation of this mechanism. And the fourth characteristic is it uses the concept of busy waiting, means we are going to write some loops in which the process will keep on checking condition, and once the condition breaks, it will enter into the critical section. So let's look at the design of this strict alternation mechanism. So we are going to first write the entry section logic, followed by the critical section, and again the exit section. In the entry section, I am going to take one integer variable called as turn. Now the current value of turn indicates if it is 0, means P0 can enter into the critical section, or if the current value is 1, then only P1 will be able to enter into critical section. In other words, I can say if the current value is 0, P1 cannot enter into the critical section because it is a P0's turn. So that's how we are going to write the logic in the entry section. And in the exit section, we are going to revert the value of turn. Let's say the current value is 0, so 1 minus 0 will be 1, and if the current value is 1, it will be 1 minus 1, it will be 0. Means if P0 comes out of this critical section, it is going to give the turn to other process, that is P1, to enter into the critical section. So the entry in the critical section is purely on the strict alternation basis. I can also say one process cannot enter into the critical section twice consecutively. If P0 first enters into critical section, after it completes its execution, it has to give the chance to P1 only. And after P1, again P0 can enter into critical section. Alright. Let me demonstrate with the help of some numbers here. So let me take the current value of turn as 0. Now as it is, the current value is 0, and if the process P0 first asks the entry section, can I enter into critical section? Now what is the current value? Which is 0, means it is P0's turn. Let the process go ahead. While P0 enters into critical section and it starts execution of critical section, meanwhile, let's assume that the process P1 arrives and asks the entry section, can I enter into critical section? In this case, entry section will again check what is the current value of turn, which is 0, means it is not P1's turn. So entry section will make the process P1 wait. Let's assume after some time process P0 continues and it exits the critical section and executes the exit section code. Now in the exit section code, it is going to revert the value of turn. The current value is 0, now it will become 1. And the process P0 will go ahead, do its some other task. Now again P1 will read the value of turn, which will be 1, and it will come to know that yes, now it is my turn and let me enter into critical section. So that's how on the strict alternation basis, P0 and P1 will enter into critical section. Let us look at the implementation of this mechanism now. So here are the shared variables I have taken. Integer turn, which is initialized to 0. Now, what should be the initial value of turn? That you as a programmer have to decide this. If you as a programmer wants to make the process P0 enter into the critical section first, then you have to set the initial value to 0. Otherwise, if you want P1 to enter into critical section first, then you have to set the initial value of turn as 1. So let me take here turn's initial value as 0 and some shared variable which is count. And here are the two process P0 and P1 entry section code in which I am going to check the value of turn for P0 as well as in P1. Some critical section code which is modifying or accessing the value of count in both the processes, and exit section code. Now let's look at the process P0. What is the logic here? While turn not equal to 0 means while turn is not mine, then keep on looping. The semicolon indicates that you have to check that condition again. So let's say the current value, if I take it as 0, 0 not equal to 0, the condition is false and process P0 can enter into the critical section. And what is the condition in P1? While turn not equal to 1 means, let's say the current value is 0. 0 not equal to 1, condition is true and it will again check that condition, means it will loop here. In other words, I can say it will wait here because the turn is not P1's. Alright. So let me explain this with the help of a program counter. Let's say the process P0 starts, executes some non-critical section code, and after some time it wants to enter into critical section. So before that, in the entry section, we are going to check the while condition. What is the current value? 0. 0 not equal to 0, condition is false and it will enter into critical section. Meanwhile, process P1 arrives and it goes and asks entry section, can I enter? What is the current value? Current value is 0 and 0 not equal to 1, the condition is true. And since the condition is true, it is going to again check the condition one more time. Again it will read the value as 0, 0 not equal to 1, again true, and keep on looping. So as of now, process P0 can only enter into critical section. Let's say process P1 completes its execution in critical section and now enters into exit section. In the exit section, earlier I have shown you, you can either write 1 minus turn or you can simply write turn is equal to 1 in the P0's code, because P0 have to give the turn to process P1. Alright, so the moment it sets the turn is equal to 1, so the turn's value is changed to 1 and it will continue with its other execution. Now after some time, let's say the process P1 is scheduled again and it will read the value of turn now. What it will get? 1. 1 not equal to 1, condition is false and this loop will break and the process P1 will enter into critical section. Let us say when process P1 is in critical section, process P0 wants to again enter into critical section. Let's say there is some loop, outer loop, via which it wants to enter into critical section again and again. So if it wants to enter into critical section again and again, it has to again pass the entry section. So let me again start the execution of P0 from here. It again asks the entry section, can I enter? But this time what is the value? Which is 1. 1 not equal to 0. Condition is true and it starts looping. Means till the P1 completes, it cannot enter into critical section. So that's how the implementation of strict alternation mechanism. Let us discuss these three requirements of synchronization mechanism. I have explained how to check these conditions. I have spent much time in log variable solution also. So let us take some programs and try to prove these three conditions for strict alternation now. Let's look at the mutual exclusion first. What is the mutual exclusion? We have to prove that only one process can enter into CS at a time. Means in our case P0 and P1 should not enter in critical section at the same time. Only one is allowed. Let me take this assembly level instructions for the entry section. Now, do you remember in the log variable solution I explained, to prove all the requirements of synchronization mechanism, you have to think not only at the higher level language code, but you have to think from the assembly level instructions or binary instructions. Because ultimately what CPU is going to execute is the binary instructions one by one. And the assumption is that preemption of a process can happen after execution of any these instructions. Isn't it? So same program again, I have just written the assembly code here. What is the assembly code? First read the value of turn into the local register R1. The instruction is load. The next instruction is compare the value of R1 with 0. And depending on this comparison, this next instruction is JNZ, jump non-zero. If the early comparison is true, then this JNZ will jump to instruction number 34. That's the meaning of this. So let's execute this code. So let me start with the first instruction at address 34. What is the current value of turn? Which is 0. So let us load in the register R1. Let's go ahead and preempt the process P0 here. So it has just executed one instruction. And now I give the chance to process P1 here. Now process P1 again, the first instruction is load the value of turn. What is the current value? Which is again 0 into its own register R1. Now both the processes P0 and P1 have the value 0 into their registers. Let us go ahead and preempt the process P1 and again give the chance to process P0. So it will compare the value of register which is 0 with 0. So what is the comparison? 0 not equal to 0. The condition is false. Means the next statement is JNZ not going to jump and the program counter will proceed into critical section. Meanwhile it is in critical section. Let me execute the process P1 again. Now it will execute the comparison statement. What value it had loaded? 0. 0 not equal to 1. Comparison is true. So next statement is going to jump to the instruction number 79. Because this comparison was true. 0 not equal to 1. Comparison was true. So again this is in the loop. Means it will again set the program counter to instruction number 77. And again it will read the value of turn. What is the current value? Again it is 0. So eventually the comparison is going to be again true, 0 not equal to 1, and again it is going to jump to the first instruction. So that's how it is in loop now. Now meanwhile let me proceed with the process P0. P0 now enters into exit section and it says my critical section execution is over. Now I am giving the turn to process P1. Now let us change the value of turn to P1 and let's assume that the process P0 again asks to enter into critical section. So if it tries to read the value of load the value of turn, what value it will load? So what is the current value of turn? 1. So it will load into the register R1. It will compare register value which is 1 with 0. What is the condition? 1 not equal to 0. Condition is true. Since the condition is true, the next statement is going to jump to the instruction number 34. Again it will read 1. Again the comparison will be true and it will keep on jumping to the instruction number 34. So that's how I can say that this process is in spin lock. Now let us look at the process P1 again. Now P1 was already in the loop and P0 has exited the critical section and give the turn to P1. Now ideally the P1's turn, the loop should break. Let's check that. So what value it will load into the register? This time it will read the value 1 and the next statement is comparison. 1 not equal to 1. The comparison is false. So next statement will not jump, means the loop has break now and the process P1 is going to enter into critical section. Alright, so with this execution sequence we proved that only one process can enter into the critical section at any given time. So that's how the first condition, which is mutual exclusion, is guaranteed. Let's look at the second requirement of SM now, which is progress. What is the progress? If any process that comes first into the system and if it is able to enter into the critical section, assuming that other process has not arrived, then we say that the progress is guaranteed. So let me explain this progress with the help of the same example. So let's take two processes P0 and P1 and let's assume that both the processes has not arrived. Let's assume that the process P0 arrives first. Now the moment P0 process arrives, ask the question to process P0, can you enter into the critical section? Because you are the only one has arrived as of now. So let us simply execute the process P0. So what value it will load in register R1, which is 0, the current value of turn. Compare. 0 not equal to 0, the comparison is false and the next statement will not jump and the program counter will enter into critical section. Means the process P0 is allowed to enter into the critical section if it is arrived first. Now let's repeat this procedure for P1 again. So let me reset the system, assume that the no process has arrived. Here just consider that the process P1 arrives now. Now this is the only process in system. Let's start the execution. What value it will load in the register? Which is 0. 0 not equal to 1. The condition is true. And the next statement, which is JNZ, is going to jump to the instruction number 77. Isn't it? Again it will read the value as 0. Again the comparison will be true. 0 not equal to 1. And again it will jump. So that's how, if the P1 process arrives first, it is not able to enter into the critical section. And that's why I say that the progress requirement is not guaranteed by the strict alternation mechanism. Why? Because P1 is not able to enter into the critical section even if it comes first. Now let's look at the third requirement of a synchronization mechanism, which is bounded waiting. What is a bounded waiting? If a process is able to re-enter into critical section, even if someone is waiting at the entry section, then we say that bounded waiting is not guaranteed. In other words, I can say, if someone is waiting in the entry section, the process which is already in the critical section should not get entry again. Because someone is waiting, isn't it? Ideally, those processes who are waiting should get the chance to enter into the critical section. Let me prove again with the help of this same program. So here first, what I am going to do, first let the process P0 enters into critical section. Okay, so straight away put the process P0 into the critical section. It will read the value of turn as 0 it will compare with 0, comparison is false. The next statement will not jump and it will enter into critical section. Now while it is in the critical section, process P1 arrives and obviously it is going to be in loop, isn't it? It's looping basically. Because 0 not equal to 1, comparison is going to be true again and again. Now here is the situation. One process is in the critical section and one process is waiting in the entry section. Now we have to ask the question to the process which is in the critical section, can you re-enter into critical section or not? So let me again come back to process P0 and proceed. So process P0 comes in the exit section, it sets the value of turn to 1. Here is the turn value set to 1 and let's execute the process P0 again and try to enter into the critical section. So what value it will load? It will load 1. 1 not equal to 0, the condition is true and the next statement is going to jump to the instruction number 34. So in short, if process P1 is waiting in the loop and meanwhile if process P0 asks the entry section again, can I enter into the critical section? The entry section logic makes the process P0 to wait. In other words, I can say process P0 will not get the entry 2 times consecutively if the process P1 is waiting. And that's why I can say that the bounded waiting is guaranteed by the strict alternation mechanism. So here, let me continue. Now the process P1 will read the value of turn as 1 and comparison will 1 not equal to 1, comparison is false and it will not jump and it will enter into the critical section, isn't it? So who has get the chance next? Whoever is waiting at the gate has get the chance to enter into the critical section. So that's why I say that the bounded waiting is guaranteed by the strict alternation mechanism. Now where exactly this strict alternation solution can be used? First thing is, this mechanism is not bad, means not wrong, because out of these 3 conditions, the first condition, mutual exclusion, is guaranteed. Okay, so let me tell you that out of these 3 requirements, the must requirement is mutual exclusion, and the other requirements, progress and bounded waiting, are purely dependent on what problem you are going to solve by the program, by your program. For example, let's say you are writing a program for some manufacturing processes, for manufacturing industry, where one process produces an item, let's say a mobile, and other task packs the item, let's say a food. There is a production of the food and there is a packing of the food. Now tell me, how can you pack the item or the food item without its production? Isn't it? So which process should get entry into critical section first? Which is the production process, not the packing process. So I can say having the progress not guaranteed is okay in this particular problem, where I want strict alternation between 2 solutions, 2 processes. Now can you think that, can I produce 2 items? Produce of item 1, produce item 2 without packing the item 1. I don't want that. I want produce the first item, pack it. Produce the second item, pack it, and so on. So that's why there should be a strict alternation between the 2 processes. One process cannot do the job twice, and that's how this solution is perfect for these kind of problem statements. And that's how we reach to the end of this topic, strict alternation mechanism. In the next session, I am going to discuss the third and important mechanism, which is Peterson's solution. See you in the next video.